Principles of Operating Systems, Chapter 10, File Organization and Management. In a multi-user system, you always have to deal with the problem of sharing files between users. Sharing files among different users raises two kinds of issues: access rights, who gets to share what, and how to deal with simultaneous access when two different users want to access or modify the same file. If different users have access to a different file, it's reasonable that not all of them have the same kinds of access rights. And it's the file management system that makes sure that the people who have given kinds of access are restricted to those accesses. There have been a number of combinations of rights developed over the years in different operating systems. The following is a fairly typical collection that would be common for most operating systems. A user might have no access whatsoever, not even to the directory that includes the file, couldn't even be able to determine that the file exists. The knowledge, the user can determine that the file exists and who its owner is. The right to execute a program, but not to make a copy of it. To read the contents of a file, including making a copy and or executing it if it's a program. Appending, to add data to the file, but not to modify or delete any of the existing contents. Update, the user could modify, delete, and add to the file's data. Change the protection, the user could give access or modify the access rights to other users. To delete, the ability to delete the file from the system. Normally, there will be one user designated as the owner of a file. Typically, that's the person who created the file. The owner normally has all of the rights listed on the previous slide, and in particular has the right to control access of other users. Access can be granted to users by classes as well. One standard class is the owner, the initial creator, with all rights to the file. They can be assigned by individual users, by user ID. The owner of the file can set up groups of users to assign rights by group rather than by individual, and files can be made public, giving access to all users in the system. Now, when multiple users have rights that allow modification of a file, to append or update the file, then it's the file management system that has to enforce the discipline necessary to avoid the kinds of access problems described earlier in Chapter 4. The structure of a file as a collection of records is dictated by the logic of the data representation. What kinds of data is being represented, the kinds of access that are going to be needed by the kinds of applications that is going to be used for. Storage, however, is dictated by the structure of the secondary storage system, the disk, hard disk. If a file is stored on disk, then the records have to be distributed in groups of blocks corresponding to sections of disk where the data is to be stored. The process of grouping records into blocks is called, of course, blocking. Application software sees the file as a collection of records whose structures are designed by the programmer, but the disk storage system sees the file as a collection of blocks to be stored in appropriate locations on the secondary storage system. The size of the blocks is determined by sector size, cluster size, the physical structure of the secondary storage system. There are three ways that blocking can be carried out. Fixed length blocking with fixed length records and an integral number of records in each block. Variable length spanned blocking, variable length records, and they are packed into blocks with no unused space. Variable length unspanned blocking, variable length records, but no spanning. Fixed length blocking, we have fixed length records. Every block contains the same number of records. Each record contained inside each A block. It's likely that the records don't occupy all of the space in a block. So there's going to be a small amount of waste space in each block. Fixed length blocking is the most common mode for sequential files with fixed length records. With variable length records, some systems will fill each of the blocks, and if the records don't fit exactly, will divide the record in between two blocks. This system avoids wasted storage space, but it's difficult to implement because, in part, records that span two blocks require two input-output operations. Further, it makes files very difficult to update. With variable length records, some systems will fill each of the blocks, storing records end to end, but will not divide records between the blocks. It would be unspanned blocking. With a system, there's going to be some wasted space at the end of each block, assuming that the next record is a little too large to fit in the remaining unused space. Records in this system cannot be larger than the size of a block. When the records of a file have been assigned to blocks, it's the file management system that has to determine where each of the blocks gets stored on disk. The system has to do two things. It has to keep track of the relationship, the locations in secondary storage that are assigned to the blocks that are assigned to files. And it has to keep track of which locations on disk have not been assigned. And so they can be assigned when a new file has to be created or an existing file has to be expanded. There are several issues involved in allocating blocks to files. When a new file is created, will the maximum space be allocated all at once? Space is allocated in sections of contiguous space, portions. What is the optimum size for portions? And what kind of data structure is appropriate to keep track of the portions that have been assigned to a file? A pre-allocation policy requires that the maximum possible size for a file be declared at the time the file is created. Unfortunately, for many applications, it's very difficult to get a reliable estimate of the potential maximum size. For these applications, pre-allocation tends to be very wasteful because users and programmers would have to overestimate the size, use the maximum possible size. So they want to avoid running out of space for their files as their program runs. Dynamic allocation allocates portions to a file when needed. Clearly, if it's possible to pre-identify the size of the file, then pre-allocation ends up being more efficient. But if you cannot get a reliable estimate on the size, then dynamic allocation supports more efficient use of the storage space. When you're choosing a portion size, there's a trade-off between efficiency for dealing with a single file as opposed to efficiency for the system as a whole. Some of the things you have to take into consideration: contiguity of space, that would increase performance, especially for retrieve next operations and for transactions running in a transaction-oriented operating system. If you have lots of portions, smaller but lots of portions, that's going to require larger tables to manage the allocation. Fixed size portions will simplify reallocation of space. Variable size and or small fixed size portions minimizes waste of unused storage. These factors interact. The two prime alternatives would be large contiguous portions, large variable contiguous portions, or small blocks. Variable sized portions avoids waste, and allowing large sizes results in small file allocation tables. Variable size allocation does, however, have the potential for fragmentation. Small fixed portions results in great flexibility and avoids fragmentation, but it does result in large allocation tables. There are three methods used for keeping track of which blocks get assigned to which files. There's contiguous allocation, chained allocation, and indexed allocation. For contiguous allocation, these simply assign a sequence of blocks to the file at the time the file is created. It only works, of course, if you have a pre-allocation policy, if you know how many blocks to assign. From the point of view of access to information in a file, this is the best way to do it. The problem is it's subject to external fragmentation. The file doesn't get fragmented, but the disk does. When you delete a file, the collection of blocks that is available is the size of the original file. And it can be difficult to find a sequence of blocks long enough for a new file. The file allocation table is simple with this system. They only need the starting point for the file, and the number of blocks in the file. It also supports random access relatively simply because it's easy to calculate the location of a given block on the disk because all blocks are the same size, and you can determine where the first block is, so you can compute where the third block is, the fourth block is. With chained allocation, blocks are allocated one by one, and each block has a pointer to the next block in the sequence. This supports dynamic allocation. It can be added, a new block can be added at any time. Since the blocks are allocated individually, there is no fragmentation of the disk. The file allocation table only requires the location of the first block in the sequence, although in many cases, many implementations also include extra information, the number of blocks for the file and or the location of the final block assigned to the file. The organization does not support random access. It's best to be used for systems where the files are processed sequentially. It doesn't support the principle of locality. There's no reason to think that the second block will be located anywhere near the first block in any given file. To alleviate the locality problem, many systems will periodically consolidate their files, reposition the blocks for each of the files to be close together. With indexed allocation, there's a separate index for each file, and each index has an entry for each portion allocated to the file. Portions can be fixed size blocks to eliminate fragmentation, or variable size to improve locality. In either case, files can be consolidated from time to time to improve locality. Indexed allocation supports both sequential and random access, and is the most popular form of allocation. A system has to keep track of what disk space has been allocated, but it also has to keep track of the space that has not been allocated, that is free to allocate. There are a number of techniques that have been developed to keep track of available space: bit tables, chained free portions, indexing, lists of free blocks. The bit table technique uses a vector identifying a block and a bit with the vector that identifies whether the block is available or allocated. If the bit is 0, that block is available. If that bit is 1, then it has been allocated to a file already. This uses the least amount of information necessary to determine whether a block is allocated or available for allocation. So it uses as little space as possible. It's efficient in terms of how much space it uses. And it makes it relatively easy to locate groups of contiguous blocks that are free for allocation. Although it takes as little space as possible, the most efficient storage possible, bit tables can be very large because storage spaces are large, involve lots of blocks. So searching the bit table can take time. Most operating systems that use bit tables keep an auxiliary data structure summarizing the contents of subranges so that it knows it can be where a location can be identified where it would likely to find space available. An alternative technique is to link the free available portions together, creating a chain. Each free portion has a link to another free portion. And in the case of the variable size portions, the length of the portion as well. This method has no space overhead. There's no need for an allocation table, only a single pointer to the first available portion. And all pointers then going to the next unallocated space to unallocated space to unallocated space. With this method, free space is subject to fragmentation. With variable size portions, creation of files can be time-consuming since each portion requires a search of the linked list until you can find a big enough space for the portion needed. Similarly, deleting fragmented files can be time-consuming as well. The indexing approach treats free space as an indexed sequential file. Each portion has an entry in the index table. With this method, each block is assigned a number and a list of free blocks is maintained. The list, the index, will typically be too long to keep in main memory, but is stored as a file on disk. That occupies a very small proportion of the space. Although the free block list will be too large to store in main memory, it can be either a stack or a queue. If it's as a stack, when a block is to be newly allocated, it'll be popped from the top of the stack, and the top of the stack will be in main memory. When a block is deallocated, it'll be pushed onto the stack. Either operation is performed in main memory, so it takes very little time. If it's stored as a queue, then when a block is newly allocated, it gets removed from the front of the queue, that'll be in main memory, and when a block is deallocated, it gets added to the back of the queue, which is also in main memory. Again, since operations take place in main memory, they're quite fast, and no disk operations are required. In either of these situations, a background thread is running, moving list entries to or from disks, maintaining optimum sizes for the main memory sections of the lists, and adjusting locations of blocks within the main list to facilitate contiguity.